Welcome. In this video I'll introduce nonorthogonal coordinates, which are coordinate systems where the, for example, x, y and z directions are not at right angles to each other. And this introduces some additional complexity, but it also makes some things much easier, particularly when you have complicated geometries or strangely shaped magnetic fields. And the main advantages of these are if you have, for example, in tokamaks, you might have a cylindrical axis, you might have a plasma shape which has some non-circular cross-section, and then you want to try and model what's happening in this machine. You now might want to have things like volume integrals. You might want to have, for example, a surface integral over some particular surface which has a shape. So you might have things like surface integrals, or you might have line integrals. For example, you might have line integrals like long magnetic fields which have a complicated shape. So they have a kind of twisting curve shape which lies on this surface. So we might have line integrals, volume integrals. So you want to integrate through the volume of this. And this becomes much easier to do if the coordinate system is aligned to these surfaces. So if one of the coordinates is along this magnetic field, for example, then differentiation or integration along this line becomes much easier. Whereas if it's in some general integration along a three-dimensional shape, then it becomes quite difficult to do. So the coordinate system absorbs quite a lot of that difficulty and makes things conceptually easy to understand once you get past the non-orthogonal coordinate system difficulty. So in this lecture I hope to try and explain how this works, so you feel a bit more comfortable with these coordinate systems. So I'll start with an example. So it's called a screw pinch. So it's like a theta pinch or a z pinch, but you have a cylinder like this, where we have z is down this axis, we have r is going radially outwards, and then we have an angle coordinates theta. For example, here we have a magnetic field. I'll draw in a different colour. So we might have a magnetic field going around across here, and it has a spiral. So B is going down there. So B has a component which is in Z, and it has a component which is around the machine as well. And so I can write that magnetic field is a poloidal component times the unit vector. And remember that because this is a unit vector, it now has no dimensions. So plus a Z component which is in Z. So B is spiraling around this cylinder. So if we want to try and work out a coordinate system where one of the coordinates is along this line, so for example the tangent vector of the distance along this line, because we want to do some kind of integration along a field line, so we would like to have a coordinate system in which one of the vectors was along this twisted sort of helical path. And so we're going to call this L as the distance. We want something where the tangent vector of L is along this gradient here. So one of the main reasons for doing this is that if we have if EL, the tangent vector, is proportional to B, then we can essentially make the parallel gradients, so B dot grad, we can make in something that looks just like d by dl. So we just have a gradient along a single direction L along the field lines. But to do this we need to make a coordinate system where one of the coordinates has a helical path, so it's following the magnetic field. So first idea we could do is define the length L to be the length along the field lines. So we define some arbitrary point where it's 0, and then everywhere from there we're counting the length along the field line. And so we can plot what that length is. If you think about plotting what a magnetic field looks like, so this is Z, and this is the distance around poloidal direction here. So this is R times theta. This is the distance, poloidal distance basically. So a field line in this case, it's just a straight line, but in general it could be a twisted curve. So L is this distance along here, and this has the same ratio as B to BZ, and here to b theta. And so L is just related to Z by this ratio of magnetic field to magnetic field in Z direction. And so we can try this definition. So we can try a coordinate system where we have the radius, we have poloidal angle, and we have length along the field line. But this still doesn't give us what we want, because if we well, basically all we've done here is just rescale the Z direction. So the EL, the unit vector in the L direction, the tangent vector, it just ends up being B over B Z times EZ. So we still have tangent vector of EL in Z direction, R and theta directions. So this is not aligned. So what we need to do is we need to find out a way of transforming to a system where if we change L by itself, we just move along the field line. And if that happens, then theta, here we need a different coordinate, because as we move along the field line, as we're following along B here, the theta coordinate is also changing. And so we need to redefine a different coordinate system where the poloidal angle is constant along the field line. So we have the because EL is just the rate of change of position with L, so keep R and theta constant. So therefore we need to find different coordinates where we have a different angle here. Because at the moment in the current coordinate system, R is constant along the field line, so we're moving along a surface, but theta is not constant. So one way of working this out is by calculating how does theta vary. And this we can see from this plot of a field line. So field line along here, this is the vector along B. And so as you move in along the magnetic field line, this R theta is changing, and it's changing by this ratio of B field to B theta. And so we have that R theta is basically changing by an amount which is B theta over B times the length. So as you move along a magnetic field, the angle is changing like B theta over B R times the length we go along the magnetic field. And so we can use this to define a new poloidal coordinate. So we can define a coordinate which doesn't change along the field. So we define new coordinate eta, and this is going to be theta, so the original angle minus this. So we subtract this component here. Because this is the amount by which theta changes as we move along the field line, and so the two will cancel out as long as we stay on the field line, as this is constant. And so now we have two coordinates which are constant along magnetic fields. We have the radius R, and we have poloidal, well, a modified poloidal angle eta. And so we have coordinates which are R, eta, and L. So a radial, a poloidal angle, and a length along the field line. And now this has a tangent vector which is along the magnetic field. So we can show this by writing down what the coordinates are. So we can write down that the next coordinate, which is R cos theta, we can just write what theta is here. So this is R cos eta plus this B theta over RB. Same, we can write down the y coordinates. So if you calculate what the eta and the L tangent basis vectors are, so you end up with the differentials of each of the components. So we just here plug in these components for x, y, and z. The position vector, this is the position as a function of r, theta, and L. And so we can take differentials of this with respect to r, this eta coordinate, and the L. The radial coordinate has two components, so it has part which is from the cylindrical component, and then part which depends on this gradient. And there's kind of a shear component which gets a little bit complicated, so we can work through that if you like. the important part is for on the flux surface, so in eta and L. So the eta direction, E eta, is just the same as the cylindrical coordinates. This is just in the theta direction, and the L component picks up 3 parts. So each of the x, y, and z has this L dependence in here, and so when you differentiate it, you end up with 3 components in x, y, and z. And this is, you can just write in terms of magnetic field. This is just the unit vector along the magnetic field direction. And so L is now aligned to magnetic field. And if you plot in a flux surface, this is the distance r theta. This is the z direction over magnetic field. It's doing this. So we now have a basis which is, and here's now E eta is so now EL is along the magnetic field, and E eta is in this direction, is in the theta direction. E eta is like that. So you see these are now non-orthogonal because the L unit vector, or L tangent vector, and eta tangent vector are not at right angles. And so when you take dot product of these two, you get a non-zero result, because these two are not at right angles. What about the reciprocal basis? So when we take gradients in this coordinate system, so we can write the gradient operator in terms of these 3 vectors. So in r, eta, and L, and then the easiest way of getting these is just the r vector we haven't changed. So this is just grad r. So eta is just theta minus this b theta r over rb times L, and so we can just differentiate that straight away. So this is just grad eta is just grad theta. It's just grad L. So in this case, we're assuming that these are just constants. So in general, we have another term in here. So we'd have a term in there which involves basically this gradient of b theta for rb, and this is essentially the shear of the magnetic field. So we have some term in here which probably L, and so give you a radial component. In this case, we'll neglect this. So if we assume that this is constant, so b theta over rb is constant, then that component disappears. We can concentrate on these components. So we have grad eta, it depends on grad theta and grad L, and then grad L over here is this E with L up is like grad L, and this just depends on b over bz times grad z. So now we have the grad L, we have grad eta, and we have grad r, and so we can write down what these vectors are. We also draw them and try and get a picture of what these look like. So grad eta is mainly in the poloidal direction, but it has this component which is in the negative L direction. And so if we plot this on this graph, this on a flux surface, so in Z and theta, so eta must be orthogonal to the L direction. So eta must be orthogonal to EL. So it must be in this direction here. So this is grad eta, or E up says eta. So E eta is in that direction. And grad L is just in the grad Z direction, so grad L is in this direction. Yeah. And you see that grad L is orthogonal to E eta, and grad eta is orthogonal to EL. And so the only components which are not orthogonal to EL, for example, is grad L. So EL and grad L have a non-zero dot product, whereas EL and grad eta or EL and grad R have a zero dot product. And you see that these components, these two different sets of basis vectors, how they behave. Okay, so then the whole point of this was to write the parallel gradients. So if you have parallel gradients along B, so derivatives. So you can write that B is just the magnitude of B times a unit vector in its directions. This is just EL, which is a unit vector along B, and the gradient. And so we're going to take the dot product of B with the gradient, so B dot grad. So EL dot, all of these components is 0 except EL dot with grad L. So that dot product with that is equal to 1. And so this just ends up being the magnitude of B from here times the parallel gradient d by dl. And so in this coordinate system, derivatives along the field line become very simple. So I skip past a few details here, and things do become more complicated in tokamaks where the field is changing. But that's the basic idea: is that you define a coordinate system where two quantities are constant along the field line. So in this case, as you move along B, R and eta are constant, and that gives you a way of calculating what the coordinates along the magnetic field, and that greatly simplifies some calculations. Okay, thank you.